It's a pleasure to me being here. And I'm Francesco Grigoli. I'm associate professor in seismology here at University of Pisa. And I mainly work on development of new techniques for characterization of natural and induced seismicity. In this talk, I'm going to introduce you new methods for offshore microseismic monitoring using very sparse network, generally because offshore seismic sequences are generally poorly monitored. So we developed ad hoc techniques that allow to better characterize seismicity occurring offshore. And I'm going to show an application to the well-known Castor seismic sequence that was induced by gas storage operation. Before to start, I would like to introduce you. It's a non-conventional, let's say, slide. This is what you see in this slide is the oxytocin. Oxytocin is a particular protein that our body generates when we fall in love with someone. And most of you will say, okay, how this is connected with seismology? Well, you will discover during this presentation why this is connected. But I can start saying that we know that this is the structure of oxytocin because biochemists and biophysicists developed specific techniques that allow to determine the structure of the protein by solving a mathematical problem called the distance geometry problem. This distance geometry problems essentially is the problems that consist in finding the coordinates of a set of points in the biochemistry, a set of atoms, essentially, by only knowing the distance with the interatomic distance and not itself directly the coordinates of the atoms. Essentially, this is because in biochemistry, it's to determine the structure of proteins, they use nuclear magnetic resonance approaches, where the biochemists are only able to estimate the distance between atoms and not their absolute position. For this reason, they had to develop particular techniques that allow to determine the absolute position of the atoms by only knowing the distance between sum of all pairs of such points, or essentially atoms. So essentially, if these are 4 atoms, what we know is only the distance between the mutual distance between each pair of atoms. But by solving a distance geometry problem, what we get is the coordinate are the coordinates of the atoms. Now, how this is connected with geophysics or with seismology more specifically? Well, also for seismicity, in analogy with seismicity, in seismological in the characterization of seismic sequence, what we would like to find is the location of each atom. Seismic sequences are cluster of seismic events that are relatively close to each other. This problem is similar to finding the structure of proteins. Essentially, a seismic cluster can be rotated, can be translated, but the internal structure of the cluster remain the same. For this reason, it's possible to use approaches that have been developed by biochemists to determine the structure to the atoms, and so we can borrow these techniques and apply to the relocation of seismic clusters. In such context, what we did essentially a few years ago, this was already published. The method that we developed was already published in 2021, and it's called HADES. HADES means earthquake location using distance geometry solvers, and it seems that this approach it's effective in the location of of seismic clusters that is recorded by very sparse network. I will show you a few examples later. So why name Hades? Most of you probably know that from Hercules that Hades is the main villain of the Disney movie Hercules. Actually, Hades is the names come from the god of underground from the Greek mythology, and Hades can be downloaded from my GitHub page. Why a distance geometry solver? Because essentially it seems that if we have a particular, it's very easy to estimate or have a rough estimation of interevent distance for two. There is a microphone open, I think, and I think it's very.
Yes, sorry. We kindly ask you please to turn off your microphones.
Thank you. So essentially, we use what we try to do essentially is to estimate the interevent distance by using a set of stations. Actually, only two stations that are more or less perpendicular with respect to the barycenter of a cluster. Why this condition? This condition has to be met because let's suppose that we have an event A here and an event B here. If we can estimate the projection along this axis by only knowing the differential TS minus TP times of the two events here. So at this station here, by just for an homogeneous medium, essentially by multiplying VP times VS over VP minus VS for essentially the differential distance between the TS minus TP of each event, what we get is this projection here. This is an approximation of the interevent distance. It's a very first order approximation. This approximation becomes better and better once phi tends to 0. Actually, when the two events lie on the same line, essentially you have if you know for a correct velocity model, you get an exact interevent distance. But this is not often the case, and generally this approximation becomes very rough when the source. The distance between the station and the barycenter of the cluster becomes smaller with respect to the interevent distance. And for this reason, we need to improve our estimation of interevent distance. We use a perpendicular station from which we can estimate another approximation on this side. Then using Pythagoras, we can get a much better approximation of the interevent distance. I would like to highlight that this is of course a first order approximation. What we try to solve here is locating seismic events with only two stations. We don't want to replace existing double difference or more sophisticated approaches. This is only an approach that can be applied when very sparse networks, when we deal with very sparse networks. So how this method works? Let's start with a very simple example. Let's suppose that we have, this method works with seismicity clusters. And let's suppose that at least for 3 points, for 3 events, we have the absolute coordinates. x0, x1, and this vector c, and x2. And for these 3 coordinates, we have essentially the interevent distance, d02 that connect the event 0 with the 02, d01 that is the distance between the event 0 and the event 1, and d12 that is the distance between the event 1 and the event 2. So we know the coordinates, and we also know the inter-event distance. So the problem that we like to solve is for another event for which we don't know the location, but for which we know using the approach that I showed before, using TS minus TP, is what we like to do is to estimate the location of this target event. Of course, so we have our reference event in blue and our target event in red. We know the distance between all the target event and the reference event, and this is the equation that we can write for each distance. And by using an approach, essentially, we solve a linear problem. We do first a rotation. So from a well-known reference frame, X and Y, we move to another reference frame that is unknown, that we don't know. It's a reference frame for which that correspond, where we put essentially at 0 the reference, the target event. The target event essentially becomes the origin of our unknown reference frame. In this way, what happened essentially? We know the reference frame. We know the location of the target event that is put at the origin, but we lose the location of the reference, or the location of the reference events. In this way, what we do by solving essentially using a singular variable decomposition, by solving this system of equation, we are able, by knowing only the distance between each event, by knowing only the inter-event distance, we can get the location of the reference frame of the reference event in this new frame, in this new frame. And now what we have the location of the reference event 1, the reference event 2, and the reference event 0 in the new reference frame, but we also know the original location. So in the original reference frame, we know the coordinates of the blue events, but we don't know the coordinates of the red events. But so returning back by rotation and translation of this cluster of 4 events, we essentially move back to the original absolute reference frame. But at this point, we get the location, because here now we have all the coordinates for the 4 events. So we just need to translate and rotate back from this reference frame to the previous one, and what we get is we get the coordinate of the target event, the red one. This is how generally the method works, and it's not very trivial, because it's essentially a system of linear equation that we solve, and this is what the biochemists generally use to determine the structure of proteins. And you apply this for many events. Now you have another event for which you want to estimate the location. Your reference frame now is composed by four reference events and 1 target event. You do the same procedures as before for many times, and at the end you get the location of many events, of all the clusters. At this point, what you do essentially is, for the 3 location, you have the absolute location. At least for 3 events, you already know the absolute coordinates, so longitude and depth. You can essentially bind your cluster to an absolute, so to do an absolute reference frame, and then locate your seismicity cluster. We tested this approach first with synthetic events. what we did essentially is we generated for different events the travel time, synthetic travel times, and we estimated the inter-event distance by using two perpendicular. In the original article, we did many different synthetic tests. This is one of the results where we used 4 reference events, so 4 events for which we know the absolute location, and 2 stations that are perpendicular with respect to the center of the cluster. And the red ones are the true location, so the location that we would like to reconstruct. And the blue one are the location that we reconstruct by using the distance geometry problem, by solving the distance geometry problem. You can see that we are able, even only using 2 stations, to properly reconstruct the cluster, the seismicity cluster. Of course, this is a synthetics. You may think, okay, with synthetics, all the methods works. But then we tested with a real example, and a particularly interesting example, because this is the Ridgecrest sequence, the well-known Ridgecrest sequence in California. The blue dots are, the red dots are the hypo-DD location obtained using more than 30 stations in the area. The yellow dots are the reference frame, 10 reference frame we use it for. We tested the approach with 8, 10, and 14 reference location that's considered okay, for which we know the absolute location. And the blue dots are the estimated, the reconstructed cluster, so the estimated location using only 2 stations, the VMF and VBS. So we essentially were able to properly reconstruct the cluster, the shape of the cluster, which was not so trivial, by only using 2 stations that are, with respect to the barycenter of the cluster, essentially have a 70 degrees of aperture, which is essentially close to the 90 degrees required by the method. This result was quite encouraging because, of course, we didn't get the same resolution that we could obtain with the classical hypo-DD location, but hypo-DD location requires many stations. Here we were able essentially to obtain very good results because we were able to properly reconstruct the seismicity cluster by only using 2 stations, and this is of course allow us to say, okay, probably this approach can use it to better constrain the seismicity locations in very poorly monitored areas. And actually, this is what we have done. We applied this approach first to the Castor sequence, the one that I will show you later, and we also applied to other offshore sequence. And one recent paper that has been just accepted few days ago was the relocation of the Adriatic sequence that occurred last year. Of course, we can also estimate the uncertainties of with this approach. We just not in order to see if by changing the reference location for which we know the absolute location, or just changing the velocity, the velocities that we use for the estimation of the inter-event distances, we can test if our solution is stable or it's very unstable. And this is what we did for Ridgecrest. We generated essentially, we resampled 25 times the velocity model by random sampling by VP values between 5.5 and 6.5 kilometers per second, and by keeping the VP-VS ratio fixed at 1.73. In this case, in this way, we relocated several times the seismic sequence using ADAS, and what we get, it seems that the results were quite stable. So we did not get we did not get. If we will have get very different, very unstable results, we will have this kernel density estimation would have been much larger and not centered in the region where we have our seismicity cluster. Finally, here a story, since it is, I just removed the slides with the reference frame because these are proprietary data and I'm not allowed to show where this occurred. I'm sorry for that. But what I can show, this is another real application of ADAS, where we started from. This is an offshore sequence. Actually, the coastline is here. So parallel to this choose station here. And this is a seismic sequence occurred in this region, in this, let's say, hypothetical region. I cannot say sorry where it occurred. And this is essentially, these are the location obtained with hypo 71, using P and S phase, using 4 stations here. Then we say, okay, we try to use waveform-based approaches, Loki, waveform stacking methods, and that is a little bit more sophisticated approach to get high resolution location. We still are using all the four seismic stations, and this is what we get at the end. We get this cluster. The cluster is much more. The seismicity now is much more clustered than this. But you can see here that still in color scale, what you will see is the TS minus TP related to this station here. From blue, which are larger, higher values of TS minus TP, to red that are smaller values of TS minus TP. This means that as far as seismicity moves away from this station, I should expect that TS minus TP values increase because they are proportional with the distance from the station. And in this case, you can see that there is not any order. These are the results of ADAS using only these 2 stations. We have an optimal condition here because it's nearly 90 degrees with respect. The 2 stations are nearly 90 degrees with respect to the barycenter of the cluster. And what we get essentially in color scale, you can see that the TS minus TP is increasing as you move far away from this station here. If I plot also the TS minus TP with respect to the station here, I will have the TS minus TP that is increasing perpendicular to this line, to the distance here. So that goes from here to here, increase from here to here. So essentially, and also in that you see that with only 2 stations we were able to correctly reconstruct the cluster. This, of course, this is a real case, and it shows that this approach was also validated with even comparing it with more sophisticated approaches. Finally, what I would like to show is the application of ADAS to the seismic sequence occurred in October 2013 in the Valencia Gulf in Spain. This seismic sequence is, I will say that it's quite famous because it was related to the underground gas storage project Castor, and at the moment is the largest event, essentially the largest event of the largest events of the sequence was a magnitude 4.3, and at the moment it's the largest event associated with such kind of industrial operation. Essentially, the Castor project was the aim of the Castor project is to store natural gas in the offshore Spain, in this region here, and store in the summer and use in the winter and resell in the winter. It was a strategic plan of the Spanish government. So this seismic sequence then occurred that was related with this project that had a huge impact in Spain. There was a trial, and the Castor project was definitely closed. However, although we know a link between the seismic activity and industrial activities, some questions remain open, because it was very hard to analyze the data set, because this was the closest station were on the coast. There was also an OBS, but the OBS was very, very, very noisy, and it was very hard to analyze the data with OBS. So the most closest station that allowed to look at the almost entire sequence, seismic sequence, are this station here, and this station here. This in reds are the about 800 events with local magnitude between 0 and 4.3. And of course, in that region before the Castor project, there was not so much natural seismicity. That's the reason why when the seismicity started, people get concerned about the project, because they were not used to feel seismicity there. And so there is a clear spatio-temporal correlation with the injection operation. And another point, interesting point, other questions remain that are related to the geometry of the fault that was activated because these are the location obtained by Istituto Geográfico Nacional, which is the seismic survey of Spain. And you can see that the seismicity is elongated along perpendicular to the coast. It's perpendicular to the coast, but the main structures faults are parallel to the coast. In addition, if you look at the waveform, you see that these waveforms are, if you calculate a cross correlation, you see that these waveforms are very similar to each other. So they have correlation values that is higher that have values that are higher than 0.8. So this 30-kilometer cloud is not justified then. I think so. This tells us that probably the cluster is much more, the seismicity is much more clustered, not so. While this is widely distributed, the main question also is this a real pattern, or is an artifact related to the fact that we have only station on this side, and the main sides of uncertainties is perpendicular to the coast as well. And the other question is, so can we estimate the this cluster here was mapped at about 20-kilometer depth, which is far away from the depth range of the wells, which was between 3 and 5 kilometers. Well, then we used ADAS, and with ADAS, what we get is this. We relocated more than 40 events. So for all events for which we had TP and TS attestation and TP and TS attestation, and what we get is this cluster here. This cluster here has a depth range about between 3 and 5 kilometers, and of course, better match the main structure of the area, the Amposta fault. And in order to validate the results, what we did essentially, we first checked the previous results obtained with Loki, the waveform-based approach. Here you see this is the Castor sequence at the events above magnitude 2 of the Castor sequence, and magnitude 3, sorry. Events above magnitude, magnitude 2, because it's this one, so the colored one. And these are the depth obtained that obtained by the IAGN. And you see that For the original cluster, the depths are larger than 20 kilometers, or of the order between 15 and 20 kilometers. These are the locations that were published in Francesco et al. 2014, where with Loki we obtained locations that are of the order of between 3 and 5 kilometers that are compatible with the injection well. And also they are much better clustered with respect to the original ones. Now, so this was the first, and this was consistent to also with the result we obtained with ADAS essentially. With ADAS, in order to check if our location were essentially consistent with the cluster shape was consistent with our observation, what we did is a check using a TS minus TP. We estimated the TS minus TP, we plotted the TS minus TP at this station here, and you see that as you move far away from the station along these lines here, the TS minus TP increase as we expect, and at the same time, the TS minus TP at this station here increase in the same direction. This means that this is the position of the orientation of the cluster is correct. Otherwise, we will not have this pattern here. So the TS minus TP that increase as you are moving away from the station. And also we performed, as usual, a sensitivity test where that still show that the results are perfectly compatible with our best estimation of ADAS. So finally, what we have done here is an application of an approach that is based on distance geometry on a distance geometry solver. It's a technique that we borrowed from biochemistry, and we adapted for seismology. The main advantage of this approach is that only require two stations that are more or less perpendicular with respect to the barycenter of the seismicity clusters. It's important to highlight that this approach works with cluster of seismicity, not with a single event in general. You need at least four events that are well located, generally the largest ones, and then you can locate the smallest ones with using only two stations. And this is quite useful not only for offshore sequences, but also for sequences that are outside the network. And it's important also to say that the most important parameter is the inter-event distance. ADAS is independent on ADAS require the inter-event distance as an input parameter. At the moment, we just used the inter-event distance estimated by the differential TS minus TP between two events. But we can improve this estimate using AI. This is what we have done as a research at the moment. We can improve these estimates using AI approaches or the CODA waves. For instance, there are methods that allow to get a better inter-event distance between using CODA wave interferometry or something else. And if we have essentially with one station or two stations, very good inter-event distance, we can reconstruct in principle any the clusters of any shape. There is also a version that a PhD student from ATTH is working on that is improving ADAS in order to work with only one reference event. So we don't need to have at least four well located reference events, but only one event that is well located. and she used quaternions to get a better location. Finally, as I've shown in this presentation, the method has been successfully applied to different cases. It was applied to, of course, a ridge crest, to another seismic sequence offshore, to the Castor case, and also recently in a paper that has been just accepted a few days ago, to the seismic sequence of the Adriatic Sea that occurred last year. And that's all. It's the results with Castors were already published in Set et al. 2021. A little bit controversial paper, probably, but at least the results of ADES were robust and confirmed that and well confirmed that the solution is quite robust. So thank you very much.